The D2MS2 talk series. Um, my name is Shuparna Bhattacharya. I'm an assistant professor in the Department of Mechanical Engineering at IIT ISM Dhanbad. I'm organizing the series in collaboration with my colleague Professor Antari Poddar, who unfortunately is traveling today. Our primary goal is to establish a knowledge dissemination platform supporting researchers interested in the data-driven modeling for mechanical fluid and thermal systems. And it's a pleasure to introduce our next speaker, Dr. Shruti Motiwale. Dr. Motiwale is currently a senior simulation intelligence research scientist at Pasteur Lab, where she works on integrating artificial intelligence with physics-based simulation. She completed her PhD in mechanical engineering at the University of Texas at Austin under the supervision of Professor Michael Sachs. Her doctoral research focused on combining finite element methods with neural networks to develop computational models for cardiac mechanics that achieved both high speed and high fidelity. Prior to her PhD, she worked as a senior CAE engineer at Tesla, where she gained experience in industry scale simulation workflows. She holds an MS in mechanical engineering from Pennsylvania State University and a BTech in mechanical engineering from IIT Bombay. Her work sits at the intersection of computational mechanics, data-driven modeling, and AI-enabled simulation, which aligns closely with our theme of this lecture series. So please join me in welcoming Dr. Shruti Motiwale. Just a quick guidelines for the audience. If possible, just please keep the questions for the Q&A session at the end. However, feel free to use the chat for questions on the go. The floor is yours, Shruti.
Thanks, Shubarno, for inviting me. This is a great platform to disseminate and, in fact, discuss knowledge about these upcoming approaches, about new ways of incorporating physics and um, uh, newer technologies like machine learning in these solutions. So, good morning, everyone. Good evening, everyone. It's actually morning here, a really great morning. Um, Amazing weather outside. So I went for a run this morning, and the whole time I kept thinking about the mechanical loads on my left ventricle, thanks to this talk that was on my mind. And why left ventricle? It's actually the chamber that takes the most load in our heart. So this chamber here, that's this rectangle. This is the left ventricle, and it pumps blood to the entire body. It requires really high blood pressure because you need to pump the blood all the way to your feet and to your heart, to your brain, and you have to overcome all of the resistance while you're pumping blood through your um, vessels. So, because of this, it faces the highest mechanical loads in the heart and hence is susceptible to more frequency of diseases. So let's look at the left ventricle a little more closely. The wall of the ventricle, the heart is a muscle. The wall, you can see it has a very muscular structure. It's made up of three layers. You have this pericardium, that's the fattest layer in the middle. The outer layer is, I misspoke. This middle layer is the myocardium. The outer layer is pericardium, and the inner layer is called endocardium. The myocardium, being the thickest layer, does most of the heavy weight lifting. Its structure looks like this. It has a number of layers, all arranged in a helical pattern. And each of these layers is composed of a number of fibers that actually change directions as you go from the inner surface, so from the endocardium, to this outer surface, pericardium. So if you cut sections at different thicknesses as you move from inside to outside, you will see that the direction of these fibers changes. Let me bring my pointer. Yeah. So the direction of these fibers changes like this. Because of this really oriented structure, you can see that the myocardium actually has a very orthotropic structure. You have this fiber axis for each layer. Then you have the sheet axis, which defines um, the plane of the sheet. And then you have a sheet normal axis that's perpendicular to the sheet plane. So this is how you define the primary directions of myocardium. Another thing I want to introduce you all is the pressure volume curve. So this faded curve in the background that you're seeing defines the relationship between the pressure in the ventricle and the volume of blood in the ventricle. And this curve defines how they are related during one complete cardiac cycle. So the part where the ventricle is relaxing, which is when it fills up with blood, that is called diastole. And the part where it is contracting, when it tightens and tries to push blood out, that's called systole. So this here. And the way this works, actually, it's really interesting to look at that. So if you see this GIF here, you can see how the ventricle is reducing in volume. That actually is a twisting motion. So imagine a wet towel and you're trying to wring it. That's the kind of twisting motion that happens. And all the fibers that we saw here in this sheet and these fibers, they tighten, and that's how they increase the stress in the ventricle, and then they try to contract the ventricle and push all the blood out. So that's what's happening in systole. uh, some important points to keep in mind from this slide are, I want to introduce you to this term called end diastolic pressure volume relationship. This is the slope of this bottom line here, and this is related to ventricular compliance. So, if you wanted to measure the effect of a disease or a treatment that affects the stiffness of the wall of the ventricle, EDPVR is one measurement that you could take from the PV loop to assess this effect. Another term I want to introduce is ESPVR, or end systolic pressure volume relationship. So this is proportional to ventricular contractility, which is the phenomena I just introduced, where the fibers in the ventricle contract and they try to push blood out. So this will change based on any treatment that affects the ESPVR or the contractility. There are certain drugs that are known to affect this relationship, and they can change the contractility. So the pressure volume curve is really important because it relates the biological or mechanosensitive effects with real mechanical function of the heart. So naturally, we want to model some of these phenomena, and computational models of the heart can help us understand diseases as well as improve treatment efficacy. Uh, because they can allow exploration of various hypotheses and treatment scenarios. For example, as we just looked, if there are certain diseases that affect mechanical function, you would like to understand how the disease could progress based on the current state of the disease. So, for example, you could try to assess the effects of um, different regions of heart attack or different extents of heart attack that could occur in a person, and how that would affect the function of the mechanical function of the heart. It can be made patient specific with advancements in imaging methods. So these days, with imaging methods like DT-MRI, we can actually um, see the exact fiber orientation of every individual's heart. And so with these types of methods, we can precisely determine what is the most optimal treatment that will result in the best outcomes for every individual patient, rather than using average flowcharts over the entire population. So this is really important, and this sounds like this is the way that we should be approaching medicine. So if it's so great, then why aren't we doing this every day for all types of cardiovascular diseases? It's actually being used in some very rare cases, but there are challenges. First of all, if we want to use simulations for these types of applications, it needs to be rapid. If you want to evaluate multiple scenarios, for example, in parametric studies, or if you want to try out a few different treatments and identify which is the most optimal one, you would like to get these results as fast as possible, ideally within maybe 15 minutes or an hour. You certainly don't want to wait 3 days or a whole week just to identify what is the best treatment to go with. Of course, because these are for medical applications, you want them to be accurate as possible, and as detailed as possible, so they can capture subtle geometric and pathological features. For example, if there is a heart attack, you really want to capture the shape and the region of that heart attack as well as possible, especially given these fiber orientations and these layered sheet structures in the heart. You want to get that right. Um, we typically use traditional finite element methods to simulate these types of problems because they are very robust, accurate, and versatile. However, they are also slow because of the typical iterative methods we use to solve these problems. They can require hours to simulate a single cardiac mechanics problem with high fidelity. And so, if you want to do multiple evaluations, this can take days and it's impractical. There are reduced order models that have been used to speed up finite element simulations. However, because we want to capture a lot of detail here, there is a potential for loss of accuracy, and they are not the ideal solution in this scenario. So, for this reason, we introduced the neural network finite element approach. Let me first list some of the novel features of our approach. The most important one is it's trained on a range of boundary conditions. So it solves not just one problem at a time, but once it is trained, it learns the solution for a range of parameters and boundary conditions. It learns a family of solutions. We use the neural network to map boundary conditions to displacement solutions. And we use finite elements to map the output of the neural network on the domain of interest to define the boundary conditions and to perform numerical integrations. However, note that the finite element method itself is not used for training. That is, we don't use the finite element method to generate any simulation data and then use that simulation data for training. That's not done. What we actually do is we solve the parametric PDE with our approach. So again, the training does not require any kind of experimental data or any finite element simulation data. So let's first look at the problem setup before going into details. The left ventricle is represented as, for a first proof of concept, it is represented as this prolate spheroid. Uh, the inner surface that you see in red, that's the endocardium. This is filled with blood, so we apply pressure on this inner surface. This top surface is where the ventricle attaches with the rest of the heart. This is called the basal plane and it is held fixed. Uh, and then yeah, so this is discretized with about 500 nodes and 1500 elements. We also specify fiber directions in the ventricle wall using a well-established rule-based method. So the fiber directions change from -60 on the inner surface to +60 on the outer surface. Then we describe the material properties of myocardium. For passive properties, which is just the stress-strain relationship of the myocardium as a non-living tissue. That is described with this Fung model. We have a very standard volumetric and deviatoric split because the myocardium is considered nearly incompressible. And then we represent active model, which is the stress-strain relationship in the ventricle as a result of the fact that myocardium is a living tissue. So that is represented by this active model. It's called the Hunter-McCulloch-Turcurs model. And this captures the phenomena of contraction. So when, as I said, when the fibers in the ventricle contract, they generate stress. So without changing any external forces, just because of the contraction of fibers, the stress in the wall of the myocardium changes. And this is what results in twisting of the ventricle, and that's what pushes the blood out. So what I want to draw your attention to here is this parameter TCA2 plus. This is the isometric muscle tension, or the tension in the fibers, and this controls the contractility of myocardium in our model. This parameter is going to come up frequently in the rest of the talk. To get the complete stress response of myocardium, we just add up the stress from the passive model and the active model to get this total stress. Now, I want to introduce an overview of the NNFE model. So as you can guess from the name, it is made up of two parts. The first is the neural network itself. It maps the pressure, so two inputs, pressure and this fiber stress, TCA. It maps these two parameters to displacements at each of the nodes in the ventricle. And then we map these nodal displacements over the complete domain with finite elements. So we have these basis functions that relate nodal displacements at each of these discrete nodes to the complete displacement field over the domain. And once you have this continuous displacement field, you can differentiate it to get your strain measures, stress measures. You can get the complete deformed field of the ventricle. You can compute the volume inside the ventricle. Essentially, you can compute all physical quantities. Do note again that all we are doing in this block is just converting discrete nodal displacements to a displacement field using basis functions, which are defined based on well-established principles of the finite element method. What we are not doing is running any finite element simulations in this block. This is just a mapping. Okay, so what is unknown here in this left block is the weights and biases, or the parameters of the neural network. And we want to find an ideal set of weights and biases that can predict the correct nodal displacements for any given pressure in TCA in our input space. So this is the problem of neural network training, to find that ideal weights and biases, the ideal set of parameters, theta star. This is usually done by defining a cost function, which takes its minimum value at this theta star. And then we use gradient descent to find the theta that minimizes f of theta. The typical cost function for neural network training is an error metric. So what you would do is you would either have access to a large amount of experimental data, or you might generate a large amount of simulation data and then compare the predictions of your network with simulation data, identify the error, and try to minimize that error. Instead, for some of these recent physics-based training approaches, the governing PDE and the knowledge obtained from the PDE is used to define this cost function. So we took inspiration from this latter approach because we do have a lot of knowledge about the physics problem. So here in this work, we use the principle of virtual work, which is a weak form of the PDE, to obtain our cost function. I imagine that for this audience, I don't need to explain this in a lot of detail. So I'll just briefly give a one-liner here. So we have this body, which is under equilibrium, omega. The displacement field under equilibrium is given by U. We have a traction force T that's acting. And we have net work done by this traction force delta W. And V is a variation to U. So it's an infinitesimal perturbation, arbitrary infinitesimal perturbation to U. And the problem statement of virtual work is to find a U such that the net work done under the action of T is 0 for all V. This is also stated in the reference configuration. You might have been more familiar with maybe this statement, where we have an internal virtual work, which is just a contraction between the second Piola-Kirchhoff stress tensor and the a variation of the Green-Lagrange tensor. So this is the internal work done. And then your external work is just force acting and then the displacement that it causes. So this is the traction force in the reference configuration, and then traction vector, and then this is your virtual displacement. And so again, we have the network, which must be zero. We redefine this in a little more detail for left ventricle mechanics. So same thing, we have the internal work, which is now decomposed into two terms because remember, our stress is an addition of two terms. We have the passive stress. Here it is just your regular um, dou psi by dou E, where this is your hyperelastic energy, which defines the material properties of the ventricle of the passive part. And then on the other hand, you have the active stress. So you get the total internal energy. And at the bottom, you have the total external work done. Again, net work done is zero. So remember, we were doing finite elements. So now we look at the discretized version where we have nodal displacements U and virtual nodal displacements V. And then H are the basis functions. So we put those in our distinct terms for virtual work. And we notice that this virtual displacement vector V makes an appearance in each of these terms. Remember that for virtual work, we have a condition that says this virtual displacement vector must be arbitrary. And so it is independent of this displacement or the integral terms. And so we can pull it out of the integral. And then we notice that the product of these two terms, so this V and the terms in the bracket, this must be zero for all V. This is probably a trick that, again, all of you are familiar with. You've seen this before. When we say that the product of V and the term in the bracket must be zero for all arbitrary V in this space of functions, then we realize that the term in the brackets must be zero. We give names to each of the terms in this bracket. So the top term is known as the passive force vector. The middle term is the active force vector, and the bottom term is the external force. And we have the residual force vector R. And we now redefine the problem statement again. So we want to find the displacement vector U such that this residual force vector is zero. Notice that the norm of R now takes the minimum value at the desired solution. So this norm of R can be used as the cost function for training our neural network. Now that we have this, let's go back to the training pipeline for the neural network. So here I'll go through four boxes that define the training for our approach. So we start with input. We generate n points in the pressure TCA space. So we predefine the ranges of interest for pressure and TCA, which is the active fiber stress. We generate n points. For each of these generated points, we evaluate the neural network with an initial guess of parameters, and we get displacements U. From these displacements, we can calculate the residual vector. We add up the residual vectors, the norms of these vectors for each of the guesses, pressure and TCA, and we get a cost function. We calculate its gradient, and we check whether the gradients have converged. If not, then we update our theta with the gradient. We give this back to the neural network, and we keep doing this until our gradient descent has converged and until this cost function has been minimized. Once the cost function is minimized, we know that the norm is now zero, which means that the displacements that it is producing for every pressure and TCA are now the correct displacements that solve our PDE. So once the neural network is trained according to this pipeline, we know that it will produce the displacements which solve our PDE for any given pressure and TCA in our input space. Okay, so with that done, now let's look at the training space. So this is a three-dimensional surface relating pressure, volume, and TCA, the fiber stress. Here, pressure and TCA are inputs to the neural network, and volume V is predicted by the model. And in a way, you could think that the method is trying to learn the surface. The model is trained over the entire functional space at once. So we generate all of these black points for pressure and TCA, and the model learns to predict displacements and hence by proxy the corresponding volume for each of these points. So it's learning this three-dimensional surface. The trained model can predict volume at any point in the training space after the training is done. So we used a densely connected MLP to train the model with 6 hidden layers, 256 neurons. Adam, we used a learning rate scheduling approach with about 500,000 iterations of training. These are just basic details. I'm going to breeze through them. And it took just 75 minutes to train the neural network over the complete functional space of all pressures and TCA. Here I'm showing the results of the neural network. So these are some pressure volume and pressure TCA loops that are predicted by the neural network. Notice that, so the red points are the predictions of FEM and the black lines are predictions of the neural network. And this green boundary is EDPVR and the red one is ESPVR. You can see that they match really well. It's indistinguishable. An important thing to notice is that the training data that we gave consisted of about 20 to 30 points, and they were arranged in a grid. But the points that we are using to evaluate the network are all of these pressure volume loops. So none of these points were in the training grid. This is what you would call validation points or test points in the traditional deep learning speak. Let's look at some more mechanically relevant results. So this is the displacement, how the ventricle is deforming during the complete cardiac cycle. You can see that it's able to capture that twisting contraction movement, deformation mode really well. The red points here are the predictions of FEM, and the solid wireframe mesh that you're seeing is the NNFE prediction. The maximum displacement error was at mid diastole, and that was just 0.8% of the characteristic length of the LV. Here I have a map of the green Lagrange strain, and again, the error was really low. You can practically see that the maps match really well. Same thing with the second Piola-Kirchhoff stress. So here, we predicted the solution for a healthy heart. Now let's look at what happens if there is a disease. In particular, we'll talk about myocardial infarction or heart attack. In India, so India accounts for 20% of global heart attack deaths. That's quite alarming. What's even more alarming is that it's not a disease of old age anymore. 50% of heart attack cases happen under the age of 50. 25% of these cases actually occur under the age of 40. Heart attack occurs due to the death of heart muscle tissue, which can be caused by a blockage in one or more of coronary arteries, and that deprives the heart of oxygen, which leads to death of the muscle tissue. And so what that means is, remember we talked about the fact that active contraction is a property of the live tissue. So that property where the fibers in your heart are contracting, causing the heart to twist and push blood out, this is the property of a living tissue. So when a part of this tissue dies, that the fibers in that region of the wall stop contracting. And so this is not going to twist anymore, or this is not going to participate in helping the entire ventricle contract and push blood out. And you can imagine how this completely changes the stress maps, strain maps, and as a result, deformation field of the ventricle and how that will affect the pressure volume loop of the ventricle and so on. The clinical treatments, and yeah, of course, as you change the pressure and volume, this is going to have an effect on your entire body because it changes changes your blood pressure and so on. So this can have several downstream effects. The clinical treatments are either medications and or surgery. So to model this problem, we make a few assumptions. We assume, first of all, that passive material properties, which is the property of the wall itself independent of its active or living tissue behavior. Those are assumed to remain the same even after a heart attack occurs. We assume that the pressure volume relationship does not change in the immediate microsecond after the death has occurred. And this has been after the death of tissue has occurred or after the heart attack. This has been validated with experiments in laboratory. So right now, for this particular talk, we are only going to be modeling this state exactly after heart attack. And when we want to think about what happens with downstream effects, we want to start modeling remodeling. So that would be the next step. Uh, the third assumption is that we assume a border zone around the infarct. So there will be a region of tissue that's completely dead with zero contractility. And then we assume a border zone where we assume gradual transition. So this border zone will have half of the contractility. We model this based on a prolate spheroid coordinate system. So the infarct is specified with the circular region with the center given by sigma and tau. The infarct has a radius r. It's axisymmetric around phi, around the major axis of the ventricle. Then we have the infarct zone with zero contractility, a border zone, which is made up of 20% of the radius that has 50% contractility. And then the rest of the myocardium is healthy, so it retains the same contractility. The mesh was refined to capture the local heterogeneous effects due to this infarct zone. And then we considered initially two infarct locations, so a basal infarct and an apical infarct. And the model was trained for one infarct at a time. We increased the training space in this case, so we included higher values of TCA as opposed to before. So this rectangular region here in the left was the additional training space that needed to be included to model the myocardial infarction. Again, for training details, I'll just highlight the things that changed. We needed a larger network in this case, so 8 hidden layers as opposed to 6 in the previous one. And we needed to, this is a stiffer problem, so we needed to train it for longer. Instead of 75 minutes, we now needed 18 hours to train over the full functional space. Now let's look at the results. So here I'm showing results for the basal infarct. Let me remind the terminology again. Basal is this top surface, so this infarct is here, and apical is the bottom region, the apex. So that's the infarct. So here is the basal infarct. We are mainly concerned about what happens at systole, end systole in particular, this region, because that is when the overall stress in the heart is the highest. That's when the whole heart has contracted completely. At that point, you can see that the displacement error is really low. So this is 0, and most of the map was completely close to blue. The maximum error occurs here again at mid-diastole, and that's mainly near the apex region. The max error was 0.19 millimeters, which is just a quarter percentage of the characteristic length. Again, for the apical infarct, if you look at end systole, you can see that the point where we really care about the displacement field, the error is practically close to 0. The maximum error was very close to diastole, and this is 0.16 mm. Again, 0.2% of the characteristic length. Let's look at the deformed shapes at end systole. Let's look at the basal infarct. So we have the cut section. Because a part of the tissue that has died is not able to contract anymore, you can expect that it's not going to twist. So when the healthy heart contracts, you see a very symmetric profile, whereas when the diseased heart contracts, you see this bulge because of the infarct. So the model is able to capture this heterogeneous effect because of the infarct. Similarly, for the apical infarct, let's look at the bottom view. So we've rotated the heart, and now we are looking at the view from this bottom. For the healthy heart, it contracts and you see this uniform profile. But for the basal infarct, wherever you have the dead tissue, that's not contracting anymore. So it remains in the original reference configuration. It will expand because the passive properties of the model are still the same. But the active contraction is now zero. So there's no rotation happening in these tissues anymore. So not only does the model capture the rotational effects, it also learns that this tissue does not contract when the contractility, this tissue does not rotate when the contractility is zero. All of this is happening because we specified fiber architectures that change directions from the endocardium to the pericardium. So the inner surface to the outer surface. Here are results of active contraction stress, comparing the FE model to the NNFE model for three different cases: before the heart attack, after the heart attack for the basal infarct, and then for the apical infarct. And you can see that it's able to predict the results very similarly. Here are the results for contractility, comparing the results with published results for an FEM simulation. And it's able to capture the behavior really well. So roughly, if we look at this, I simulated it for a similar extent of basal infarct. And you can see that it's capturing the fiber stretches. So now I literally measured the stretch lambda for each of the fiber in the heart, and it's able to get that derived metric correctly. And similarly, it's able to get the active stress correctly. So this is a really promising result that even with our very idealized shape of the ventricle, we are able to capture not only the direct results of the heart, maybe the displacement field, but also these derived metrics like fiber stretches or active stresses. It's able to predict the general trend of what's happening in the heart in a very strong physics sense, because it can predict direct results and also derived results that can match with published results. And note that these published results for this realistic heart have been matched with experimental data. So this shows the predictive power of this method. Um, Now I'm showing the contractile response of remaining normal myocardium. So this dark red region here, that's the healthy myocardium. If you plot the uh, contractility or TCA value in this myocardium, and if you compare it with pre-heart attack, you notice that the contractility increases relative to the pre-heart attack situation, which actually makes a lot of physiological sense because the heart wants to preserve the same amount of ejected blood volume. And so as a result, the rest of the myocardium needs to contract more because this is not contracting in order to generate the same pressure and to eject the same amount of volume of blood. Again, here I'm comparing these results with published FEM model, and we are also able to um, match the trends with the published model. What's important here is, so these curves, these types of curves, like the changes in pressure volume curves or the changes in contractility, are actually the results that doctors care about and that they would be looking at when assessing the effect of a treatment or assessing how the disease will progress and have effects on the health of a person. So the model is able to predict these types of physical results. With that, I would like to conclude and give a summary of the approach. So the NNFE model solves the parametric PDE directly. That is, it learns the map between parameters, in this case, pressure and TCA, and the displacement solution. And it is based on the well-established finite element approach. The training process does not rely on running any finite element simulations or any experimentally generated data. The model is trained over the entire functional training space only once. Once trained, the model can produce the results for any pressure volume path in the training space within 30 seconds. So the one single cardiac loop that we saw, that consisted of about 32 evaluations for every pressure volume state. So that takes 30 seconds. And the model can reproduce the results for both healthy and diseased states. One of the most important future direction is the extension to realistic left ventricle geometry. So from a previous continuation of research, we have access to extensive physiological data set of a single ovine heart. And the next graduate student in my lab is now working on extending the NNFE model to this realistic heart. So we have access to image-driven data. So basically, real fiber orientations in an ovine heart, data for pressure volume loops, data for action potentials, which define TCA, echocardiography data, and all of this realistic data, medical data that doctors are interested in looking at when evaluating a patient. So the um, current direction is to extend this model to apply it to the ovine data set and try to match this experimental data. So with that, I would like to conclude my talk. I would like to acknowledge my advisor who has been phenomenal in guiding me through my PhD and my colleagues and the funding sources. And I'm happy to take questions.
Thank you for the awesome talk. Um, I have a few questions, but I will ask the audience to go first. If any questions, feel free to um, unmute yourself. You can also type the question in the chat. Um, whatever works for you, please feel free to go ahead. Yes,
I
Krishanu, please
see a
go
raised
ahead.
hand.
Yeah, please go ahead. I see another video as well. Um,
I have a
Hello, Shruti. Can
question.
you hear me? Can you
Yes.
hear me?
yes, yes.
Hello, Shruti. Thanks for the nice talk. So
Mhm.
my question is kind of a clarification. So in finite element, is usually done is we reduce the residual through a Newton-Raphson method or something like that. And here we are using the neural networks, right?
Mhm.
Okay.
Yes.
And so do you have any estimate for example, you mentioned it takes like 30 seconds to get any data once it's trained. And how long does
Mhm.
the finite element simulations take?
Yeah, so each simulation so for the whole pressure volume loop, it took us 30 seconds. The finite element simulation took, I think, 7 hours because of exactly that iterative approach. So
Right.
every time you give it a new pressure and TCA, you
Mhm.
need to do this iterative approach. And another trick here is the experimental data that you have access to is actually pressure and volume,
Mhm.
not pressure. TCA is not something that you can measure very easily in the
Okay.
lab, not
Mhm.
on a living person. So
Mhm.
you actually need an inverse problem here to get the
Mhm.
TCA. But volume cannot be an input to your PDE. The input to the PDE is TCA. So you
Mhm.
also have an inverse problem
Mhm.
embedded here.
Understood. Yeah.
That's why the finite element method takes so long.
Mhm. And so another question I have is, so for finite element methods, there one can change the, for example, material properties, and they can use different materials in different parts. Could that be done in neural networks as well, or is it just a single material that has been considered for heart here?
Great question. Yes, so that is definitely the second natural progression here. It's not that tricky because you can easily just add more parameters to the input
Mhm.
space. Um, but right now, yeah, right now the material properties are fixed. But the idea when we deploy this
Okay.
would be to change material properties. And then another extension that is a
Mhm.
natural question here is what about geometry? That is also fixed.
Correct.
So for that, we have been using what is called as NURBS. So NURBS allow you to use geometric parameters of your shape. So for example, in this case, they would be the length of the ellipsoid or radius of the ellipsoid. And you can have
Mhm.
similar geometric defining parameters for any shape of the heart.
Mhm.
And those parameters can then allow you to generate like a predetermined shape and mesh of the ventricle. And those can now be the inputs to your neural network. So we've already started working on these things. It's not published, so I cannot present it today. But yeah,
Sure.
with
I
NURBS and
understand.
with changing material properties, you can incorporate all of these variations in the training pipeline.
Okay, thank you.
So we have another question in the chat. Pawan, you can also ask the question. I think you were trying to ask it, but anyway, the question is, any results that guarantee NN size is sufficient for a particular error threshold for this model?
Yeah, let me see if I have it here. Yes. So we did a comparison of different network architecture sizes. I'm showing 4 here. There wasn't a huge difference here, but we found that the best results for not just the displacement field, but also for all the predicted results like strain measures and stress measures. For that, this 256 by 6 layer was the best. We tried different shapes and sizes. So we have this another network with 16 neurons in each layer, but then we had a much deeper network. And we used all the uh, standard tricks that are needed for a deep network. So we had some skip connections that made sure that the 16 by 16 network isn't plagued with exploding gradients or vanishing gradients and all of that. Uh, and then we used other networks which had less layers but more neurons in each layer. And more neurons, more layers, everything at the same time. You do see some benefit with this red network here, but it's not worth the amount of extra training time that it took. So 256 by 6 for the healthy heart, this took only 75 minutes. So 1 hour, 15 minutes to train over the entire functional space. Uh, and it was able to predict good enough results. So again, because this came up, just to juxtapose. So 1 hour, 15 minutes for the neural network to train over the complete functional space for all pressures and TCA versus the finite element method, which took about 6 hours for a single pressure and TCA evaluation. So some of this comes from the fact that we have some more efficient training methods like gradient descent, which is smarter compared to the iterative methods that we have to use in FEM. And because this is an inverse problem, each evaluation with NNFE method is much faster, whereas for the inverse problem with FEM, you have to do the iterative method 32 times for every inverse problem. So it's, I mean,
That's
FEM
expensive.
with its iterative method is just not the right method here.
Right, right. Any other questions?
I have a question.
Yeah.
Hi, Arsha.
Hi, great to see you guys.
Great to see you again.
And thank you for the presentation. I have a question. In your expert opinion, what are the limitations of using neural networks in FE, and how easy it is to translate this approach to other bio applications? Kind of two questions
Yes.
come over.
So in terms of transferring this to other bio applications, I see really not a huge difference. The main thing you would have to change is the material properties, of course. And then in terms of geometry, I already addressed that. Actually, this material, the heart, is one of the most complex biological tissues because of the complicated fiber structure and the orthotropic material property. So these approaches, similar and easier approaches, have already been applied for the skin. I think even brain is another potential application area. Our lab has already explored the application of this to the breast tissue, but you don't really, I mean, it's a simpler problem in a way. With cancer, with the possibility of cancer and how that changes the properties of the tissue, this would be another great application there. And then in terms of limitations, so I wouldn't say there are limitations of this approach, but I'm biased. But I do see mostly advantages. I think what one needs to keep in mind when applying these approaches is using it for the right kind of problem. So if you were going to train this if you were going to apply the NNFE method in a scenario where you don't have this inverse problem that you have in this situation, right? Because TCA cannot be measured. So if you were comparing training time plus inference time with a forward problem, that's a bad application area. That's where you should be using the original FEM. You should look at the right application area. So if you have an inverse problem, or if you want, like if you really have a speed issue that needs to be improved, and if you have a parametric situation, you need multiple evaluations, that's when the NNFE method or any other ML method shines.
Correct. And this NNFE method, once it's trained and ready, are they real time in kind of giving you the solutions? Or
Yeah, pretty much. So for this one cardiac loop where we had 32 points, where is it?
Mhm.
Give me a second. Yeah. So this is a pressure volume loop. For
Yeah.
this curve represents one cardiac cycle. So we discretized it with 32 points, and it took us less than 30 seconds to evaluate this one.
Yeah. Okay. Awesome. Thanks.
Yep.
So I do not want to bombard you with more questions, but there are a few,
Mhm.
just a few. So let me see which one I want to ask. So the first one is that I think you already addressed that question, is parameterizing the geometry itself through
Yeah.
um,
NURBS.
NURBS.
Yeah.
There is, I have seen other approaches. For example, you can perhaps like if you have the data, uh, like the temporal data, it is perhaps also possible to extract the POD modes or like from this data that also represents the volume itself. Uh, so just like NURBS, it may be possible to represent this volume uh, as a linear combination of the mode shapes.
You could get volume, but if you want to go back and think about all the evaluations that a doctor and like additional things that you might want to look at, if you have this NNFE method, if you can simulate the entire geometry, you can see how targeted treatments, such as if there's a heart attack and if you want to give drugs in a certain region to change contractility of the myocardium, you might want to see targeted changes in stress distribution and strain distribution. So sure, right now, doctors are only looking at pressure and volume data to make diagnosis because they don't have access to anything else. But if we can give them the entire stress distribution and strain and like local heterogeneous effects because of their treatment, that's more information that they can use at. I
No,
don't
no,
know if I
that
went on a
is fine.
tangent. Yeah.
No, that is fine. I'm just saying that instead of NURBS,
Mhm.
I'm just talking about geometric representation. It may be possible to represent it through mode shapes as well. And then you may be inferring the parameters instead of the nodes. So the parameters are the parameters for linear combinations of those mode shapes. That
Okay.
will reduce the nodes.
I see the yeah, instead of having all the number of nodes, the output layer will reduce. Yeah. Yeah,
I
that's
mean,
certainly
similar,
possible.
very
Yeah,
similar
it's
to
similar.
nerves.
Yes.
I mean,
Yes.
it's the same. And then did you also
So I
think of a?
think there
Mhm.
would that would be one way in which we might be making this problem more efficient for
Hmm.
this particular application, but then it won't remain generalized for applications to other um, medical applications. So you won't have access to a volume for a breast tissue, maybe.
Right, it will be customized because POD
Yeah, it
modes
will
are
be
tailored
customized.
to the
Yeah,
case.
yeah,
Yes, absolutely. So
yeah.
that is true. And your approach is similar to pins, right? So you are not at all looking at training data. It's just the residual based
Yes.
training,
Yeah.
right?
So Professor Demkovich at Odin Institute refused to call it training. He considers it a parametric solver.
Hmm. Makes sense. Makes sense.
Yeah.
Makes sense. And do you also plan to apply graph neural networks? It seems like a very uh,
That's
uh,
my personal future interest here.
hmm,
Now that I've been working at Pasture Labs, I
hmm,
have much more broader exposure, and I
hmm,
realize that MLPs are very primitive here. So yes, graph neural networks, I think, would increase the representation power of this method immensely. Yeah, that's something that I want to try on my own.
makes sense. Makes sense. Okay, but it was really enlightening. Uh, Very, very articulated talk. Thank you so much.
Mhm. I hope
I have one
everybody
last
else found it
question.
useful.
Just
Thank you for
a
inviting
second.
me.
No, no, it was great having you. Any other questions, audience?
I have one last question,
Okay.
Mhm.
time allows. So, since you have more expertise in this neural network field, I wanted to know what's your opinion on using this in this type of NNFE to plasticity type of problems, which has been used in FEM quite well.
I think this would be really helpful there as well. Again, because of the amount of nonlinearity involved in these problems, when nonlinearity comes into FEM, and when we think about discrete problems, iterative methods come into picture. And every
Right.
time iterative methods come into picture, you have speed issues.
Mhm. Right.
So
So,
even in, yeah.
please go ahead.
Even in cardiac problems, we have growth and remodeling, which is
Right.
when you, like the problem formulation is not too different. And in NNFE methods, in fact, the power of these methods becomes more and more apparent. It scales non-linearly as you go into more and more non-linearity in your
Okay.
PDEs.
So what I'm trying to understand is you mentioned that this TCA parameter, which is difficult to calculate or difficult to measure, which is where this NNFE is helpful. Could we consider like plastic strain or growth as a parameter, where this NNFE would be helpful? I mean, is there any similarity there? Like for
Not
example,
for TCA in particular, because TCA is not plastic strain. TCA is it's actually related to some of the chemical reactions that happen at that level, and that changes in every cycle, that changes the
okay.
stress of the fiber because of this chemical
Mhm.
reaction. So plasticity would be something that keeps accumulating over time. But that also
Right.
happens in a heart. That also happens, especially with heart attack. Over
Mhm.
time, the passive properties of the myocardium start to change because the heart has to continually contract and
Okay.
continually
Yeah,
pump more
I
blood.
understand that
Yeah.
it's not exactly plastic strain. What I'm trying to understand is for plasticity, plastic strain is an internal parameter. For growth tensor is an
Yeah.
internal parameter.
Yeah.
Is TCA similar, used as an internal parameter in just pure finite element simulations, or is it something differently treated where there is pure finite element simulations that you did for comparing with the NNFE?
Um, can you explain what you mean by an internal parameter?
By internal,
I
I
think,
mean that is, for example, when we are solving for displacement in a plasticity problem, we are solving for displacement and plastic strain, both
yeah.
with
Yeah.
iterations. So
Mm-hmm.
plastic strain is an internal variable that is being evaluated at, say, quadrature points or nodal points. Is it
I
something
see.
that is
No,
also
this
done
is
for
actually
TCA?
it's a parameter in the PDE itself. TCA shows up in your equations for active strain. And
Okay, I see, I see.
yeah, it's a,
Okay, understood. Okay,
I
thank
forgot.
you.
Yeah, let me see if I can show you the material properties again. It shows up in your constitutive equation.
Oh, I see.
Here.
Okay, got it.
Yeah.
Mhm. Got it. Okay, thanks. It was a very nice research and presentation.
Thank
Good
you.
to know.
Very, very informative. Thank you so
Yeah.
much. Okay, so I will not hold you for longer. Thanks again for joining and giving this great presentation. Um, and we'll keep talking, I hope.
Yes, of course.
Yeah.
Absolutely.
Okay. Okay. Thank you. Have a
Thanks for
great day.
inviting me. You
Yep.
too. Bye.